and split bounds.
Okay, thank you. So this is joint work with Beniamino Acatoli and Stéphane Graham-Langdon, both from École Polytechnique. So the idea of this work is to understand what is a quantitative type system. So quantitativity is a concept emerging in different areas of computer science, and we would like to give at least a first answer to this question. So I will discuss some issues related to that. In order to understand quantitative type system, the starting point is to understand intersection types, because quantitative type systems are intersection type systems. And this can be explained in contraposition to simple types in this way. So the first issue is that in simple type theory, you only have a functional operator to construct types. In intersection type theory, you also have an intersection operator, which is giving a kind of polymorphic or polymorphism, because you can now type a term with an intersection type. That means that you will give two different types or more than two different types to a term. So while simple type theory comes from a logical point of view, typically the Curry-Howard correspondence, intersection types come from the notational semantics. And that's why typically in simple type theory you can show that a typable term is normalizing, and that's all. But using intersection types, you can also show that the terminating term is typable. So that's why typability is undecidable in intersection type systems. But even if you have undecidable systems, the technique is quite powerful to reason about different operational properties. That's what I'm going to explain now. So just to fix things, a typical example of a term which is typable with intersection types but not typable in simple type theory is the auto-self-application function, lambda x, x applied to x. So this is typically a term which is typable and terminating at the same time, and so you will find this in intersection type theory. So now what is the intersection operator? The intersection operator has some properties, typically associativity and commutativity, but there is a choice to be done between idempotence and non-idempotence. So there are two different schools or ways to deal with that. On one hand, you have the classical intersection type theory pioneered by Copo and De Zani, the Torino school. And on the other side, you have linear logic, which has a resource-aware flavor in which the intersection, which can be seen as the tensor, is taken as non-idempotent. So on one side, you have sets because you have an operator which is associative, commutative, and idempotent. And on the other side, you have multi-sets because the non-idempotency gives you a structure where the number of occurrences of a type in another type, which is a multi-set, is crucial. And this gives the possibility, so this is an example which is x applied to x applied to x. So in the idempotent world, you will need one type to type the x which is acting as a function on the left-hand side, and just one type will be sufficient to type the two arguments x, the one in the middle and the one on the right-hand side. In the non-idempotent case, you will type, of course, the left-hand side x with a functional type, but you will need two different occurrences of the type A in order to type the two occurrences of x in the term. So that's a very simple example, but that illustrates the main idea of quantitative types. So another interesting issue is that things that are undecidable in the idempotent world become decidable in the non-idempotent one. Typically, the inhabitation problem, which is a problem such that giving a typing, you want to find a term such that this term is typable with the typing given as input. So this problem is known to be undecidable in the idempotent world, but it becomes very trivially decidable in the non-idempotent one. And more importantly, in the idempotent world, you show intersection types to prove qualitative properties of higher order programs. So I will explain this in more detail. And in the non-idempotent world, you can make these properties more interesting because you will infer also quantitative information about these properties. So you can bound and measure things, and that's become more exciting and more interesting. So first I will review some basics about how to use idempotent types to characterize and bound typically operational properties like normalization. I will mention some more examples in the literature, and I will explain which is the exact contribution of this paper, which concerns exact measuring and not only bounding operational properties. So let's start with by talking about operational properties. So typically we want to talk about normalization, and there are a lot of notions of normalization around. So for example, we can say, well, given a term, I would like to know if there exists a path evaluation going to a result. This is one kind of operational property. Another kind of property is, given a term, I want to know if every evaluation path goes to a result. This is another kind of property which is much more involved, because for that I need to inspect all the evaluation paths going to a result. So we want to deal with properties like that, and for that we need to be precise and to understand what is a result, what is the notion of result. So there are different notions of result. There is no only one notion. For example, if you work with programming languages, maybe you will be interested in head normal forms, or if you work with proof assistance, maybe full normal forms are more appropriate. But in any case, given a notion, a fixed notion of result, then you can define your property, and there are different kind of properties that you can define. Typically, a term is head normalizing if and only if there exists an evaluation path to head normal form, weakly normalizing if there exists one to full normal form, strongly normalizing if every path goes to full normal form, etc., etc. So taking into account these properties, you can make some structure the world of lambda terms. So you have, or pure functional programs, if you prefer. So you have a whole set with untyped terms. You know that inside this set, there is the set of simply typed terms. These terms are in principle included in the set of strongly normalizing terms, which are in turn included in the set of weakly normalizing sets, terms, etc., etc. And all this is defined by using these operational properties that I have defined before. But now, how the typing systems are used here? Well, the action is very simple. You want to color the green circles by using the yellow color. Why the yellow? The yellow one is used here to talk about typability, and the green one is used here to talk about operational properties. So there is a typing system being able to color the set of strongly normalizing terms with yellow. That means that there is a typing system allowing to show that the term is typable if and only if it is strongly normalizing. In the same way, we can paint with yellow the circle, the bigger circle, because there is a typing system such that a term in the system is typable if and only if it is weakly normalizing, and so on. This is the kind of game that we are playing. So in this way, the dynamic property becomes, in some sense, a static property, because we are now capturing this property by using typing systems. So I'm not going to show any typing rule at all. I'm going just to give a very simple example to give you some ideas and some intuition about quantitative typing systems. So this is a very simple term, the church numeral, the 3. And if you want to type this term using idempotent technology, then you will find something which is close to simple type theory. So you give to F one type, which is a functional type. You give to X another type, and then the function is typed. In the non-idempotent case, you need to give to F 3 types. Why 3 types? Because in the number 3, F appears 3 times. Of course, you cannot guess the number of times that the variable will appear during all reduction sequence, and because the system is undecidable. But the idea is that in the typing system, you are encoding information which is necessary to compute the normal form of the term. Well, now let's understand what is the difference between the qualitative properties that we have in the idempotent world with respect to the quantitative information, quantitative properties that we can get in the non-idempotent world. So typically in intersection type theory, you can not only show substrate reduction, which is a property that you usually have in almost all respectable typing system, but you also have subject expansion. Subject expansion says that typability is stable by anti-reduction, while substrate reduction says that typability is stable by reduction. So in order to, when you want to transform or to interpret this in a quantitative world, you still have stability of typing by reduction and anti-reduction, but you also get a measure. And the measure is a measure given by the typing tree derivation. So the quantitative version of substrate reduction and substrate expansion gives you a measure which is strictly decreasing. So if there is a figure to keep in mind from this talk, is this figure here, which says that quantitative typing systems give you measures which are usually strictly decreasing or at least decreasing. And so this measure gives you an upper bound which is extracted from the typing derivation, but this upper bound is talking about something which is happening during reduction. So typically here, the number of nodes, if you want the number of application rules of the typing derivation, gives you an upper bound to the length of the evaluation path starting at a given term, okay? So another typical case of a qualitative property that we transform into a more interesting quantitative property is the typical theorem saying that a term is typable if and only if it is normalizing. Of course, it depends on a precise notion of typability and a precise notion of normalization. But to be general, let's take this in a very general way. And so in a qualitative world, that means when you work with idempotent types, you can show the theorem in particular by using substrate reduction and reducibility candidates in order to infer that a typable term is normalizing, okay? So this is a typical proof of normalization. On the other side, you have a quantitative theorem saying the same thing but adding more information. The quantitative theorem says that to be typable in a quantitative type system is equivalent to being normalizing, that is, that exists a sequence going to normal form, but also you have information about you have quantitative information about this reduction. And which is the quantitative information is that the number of nodes of your typing derivation is an upper bound for the sum of two things. On one side, the length of the reduction path, and on the other side, the size of the normal form, okay? So in order to show that the typable term is normalizing, you don't need any more reducibility candidates. Why? Because you have the quantitative version of the substrate reduction property, which says that if a term is typable and you reduce it, then there is something which is strictly decreasing. And this measure is just based on integers. So you know that if you have a typable term and you reduce it, at some moment this is terminating. This is a trivial proof of termination for lambda calculus. So there are many, many examples in the literature using this kind of ideas. So you can do that in the intuitionistic, you can do that in particular in the intuitionistic case, that is in the framework of lambda calculus, with different versions of lambda calculus, call by name, call by value, call by need, etc. But the idea and the model is extensible enough to capture also other frameworks, like, for example, call by push value, or lambda calculus with resources, or calculi with pattern matching, for example. In all cases, you obtain upper bounds. And so now we will try to be more precise and to improve these upper bounds. And the idea is quite simple. If you want to obtain from an upper bound an exact bound, when you inspect your typing derivations, you need to take a tight one. A tight one is, in some sense, a minimal one. So if you have minimal derivations, then the size of this typing derivation gives you exactly the sum of the length of the reduction sequence of the term to normal form and the size of the normal form of the term. So the typing system is guessing some information about evaluation. This is quite interesting. But the problem here is that you obtain an exact measure for two things, which are the length of the reduction path and the size of the normal form, which are in principle not really related. And why not? This is known as the size explosion problem. So the size explosion problem says that there is a term, there is a program having an exponential gap between the length of the reduction sequence and the size of the normal form. So it is not very interesting to count these two things together, because it could be that there is an exponential gap between these two things, okay? So here is the case of the size explosion problem. You have a short path going to a big normal form, but you can also imagine a dual situation where you have a very long path going to a very small normal form. And in order to face this problem, we decided to split the measure, and in order to count only by using the size of the typing derivation, we add to the typing judgments, to the typical typing judgments, two counters, one in red and another one in blue. The red one is going to count the length of the evaluation path of the term to normal form, and the blue is going to count, or to guess, if you want, the size of the normal form of the term t. And so the kind of theorems that we obtain in the paper for different notions is like the one here. Given a term which is typable by using a notion of minimal derivation, which is called tight in the paper, and using these two counters, the red one and the blue one, being typable in this way is equivalent to being normalizing. That is, there exists a sequence going to normal form, and moreover, the red counter, corresponds exactly to the length of the reduction evaluation path going to normal form. The blue counter corresponds exactly to the size of the normal form, and the sum of the two counters corresponds exactly to the size of the typing derivation. So this is a dynamic information extracted from a static tool, which is a typing derivation. Okay? Now the length and the size are measurable in an independent way. And so we did it for different strategies for lambda terms. So typically, we have done this for head reduction, for leftmost reduction, and for maximal reduction. Maximal reduction is a kind of reduction which is perpetual. I mean, it keeps non-termination if the term is non-terminating. But of course, it terminates if the term is normalizing. And we have also investigated this kind of techniques by considering the other terms than lambda terms. In particular, we consider terms with explicit substitutions. These terms are interesting because on one hand, they are used, for example, to encode abstract machines, to specify abstract machines. They can also be used to encode some logical objects like proof nets. And when you use other syntaxes, of course, your counters, you need to change the notion of counters. So, for example, in the case of lambda terms with explicit substitutions, we have 3 counters. And so the first one counts or guesses, if you want, the length of the multiplicative steps to normal form. Multiplicative steps are those that break the beta radixes. But we can also count separately the number of steps which perform substitution. And of course, we have also a counter for the size of the normal form, and the sum of all the counters is always it's equal to the complexity of the typing derivation. So once again, this is a way to capture a dynamic property by using a static tool. And by this time, when you use quantitative type theory, you provide also quantitative information about different properties, operational properties of your terms. Okay, so it's time to conclude. On one hand, I would like to emphasize the power of non-idempotent intersection types. So I didn't have time to talk about other things that we can do with this kind of systems, as for example, to reason about observational equivalence of different languages. Typically, you know that call by name and call by need is equivalent, but the proof, I mean, is quite involved because you need to use a heavy theory of rewriting. But if you use intersection types, you can prove in a very, very simple way that call by need and call by name are equivalent. So this is the kind of things that you can do. And as ongoing work and further work, there are many different features of programming languages that we would like to consider. And there are some particular cases which are very challenging. On one hand, it will be interesting to understand how to deal with general rewriting because lambda calculus, for example, is just a very particular case of higher order rewriting. So it would be interesting to understand how to capture other notions of rewriting. And another challenge, I think another challenging case is call by push value, because usually call by push value is able to encode call by name and call by value. But when you apply these techniques to call by name and call by value, you usually use different typing systems to deal with them. So there is one which characterizes properties in call by name, another one characterizing properties in call by value. So it will be interesting to understand if there is some typing being able to capture call by push value in a very precise way to understand what is happening there. Okay, thanks for your attention.
We have time for a couple of questions. So the questions the most of us are interested in is whether the for all quantifier in system F can be understood as an infinite intersection type.
Well, so it can be understood as an infinite polymorphism, okay? But here the issue is that we have a kind of polymorphism which gives you characterization of normalization, which is not the case of system F, okay? So this is an important difference.
All right, another question. Have you thought of adding intersection types to more expressive systems such as calculus of constructions?
Okay, so, well, the ideas going on are on this slide. So The first step would be to understand already, I think, well, a first step, the calculus of construction is intuitionistic, so I was particularly interested in control operators because I think that it's a framework which is really interesting to be integrated in real programming languages. Then in others, if I want to face the calculus of constructions, maybe I would be interested in the calculus of inductive constructions. And so I think that to understand general rewriting is a key point to be able to face the calculus of constructions.
All right, the last question. Do you know of any programming language that implements intersection types?
Well, I know that there are programming languages used to deal with data, which use decidable fragments of intersection and union types. And so there are some works, for example, by Giuseppe Castagna in this direction. But of course, in this case, you need to restrict the power of intersection types because you want to be decidable, okay? So you restrict the power, and in this case, you don't capture anymore, you cannot characterize anymore normalization properties, for example.
All right. Thank you, Delia.